and you might learn something. So we are on page 95, relative velocities. No, Cal's going through. Did I say that joke already? Relative velocity. Thank you. Thanks, Rachel. Appreciate it. So page 95 says, Tarzan and Tarzana are brawny ape people. I have no idea what that means. They're brawny ape people.
They're like big and like
Yeah.
strong.
But like, what difference does that make? And when it says they're ape people, does that mean that they were raised by apes, or that they're like some sort of human ape hybrid?
Like Tarzan, he was raised by apes.
Well, yeah. Well, you would think so, but shouldn't there be some sort of copyright violation, or maybe it's public domain? I don't know.
I once was doing this math thing on this site, and it asked me to like. It was talking about that Hermione's and Harry's length of their wands.
Oh.
Okay. Like, what?
Can I say that? Yeah.
Really?
All right. So, anyways, Tarzan and Tarzana are brawny ape people, and they decide to have a race across the river. Both are excellent swimmers and have the same ability, which means they can swim exactly at the same speed. So why are they having a race? See what I'm getting at here? Tarzan swims straight across, landing on shore directly across from where he started. Tarzana jumps in and points herself across the river, but ends up farther downstream where she reaches the other side. So, in other words, Tarzan, it looks like this. Tarzan jumps in. He aims this way, but he ends up going straight across. I can't even abbreviate them with T's because Tarzan and Tarzana.
T1, T2?
T1 and T2, exactly. So he jumps in, he aims that way and goes straight across. She just decides to swim straight across, but so she ends up like this. Which way is the river going? The river's going this way, right? Okay. Tarzana jumps in and points herself across the river, but ends up farther downstream where she reaches the other side. The two are pictured below in figure 324. Then just to make things even more interesting, well, it first says who finished first. Well, who made it across the river first? Remember, they can swim at the same speed. So does he get across faster if he points himself upstream but goes straight across? Or does Tarzana get across first because she doesn't care about the current and just ends up going downstream? What do you think?
Same time.
Same time? Good morning. For computer science, he just needs a computer. Yeah. He can come up probably pre-5, probably the best. Yeah. Okay. You think they arrive at the same time, Josh?
Yeah.
Okay.
Using like current.
Okay. Fair enough. Who swims farther distance? T2 for sure, right? Going at an angle. Okay. So then it says, then there was Cheetah, faithful brawny ape pet. So what is he?
He's a cheetah from the movie Tarzan.
But he's a faithful brawny ape pet. So is he like an ape? Is he like a dog that's just like a
cheetah?
Don't you remember the funny joke when they were like, he's a cheetah, but he's not really a cheetah, he's a monkey?
Yeah. Well, it says, I know Cheetah from the Tarzan books is a monkey. Why doesn't it just say their monkey or their pet monkey? But no, faithful brawny ape pet. Makes no sense. He chose to swim across the same river but at a time when the floods were raging and the river flowed at 5 times the velocity it did when Tarzan and Tarzana swam. Cheetah 2 is a good swimmer and has the same ability as Tarzan and Tarzana. Did Cheetah finish the crossing in a shorter time? These questions will be answered in the next section. Sounds like next week on weird people that live in the forest. So Cheetah swims, the river's going faster, so he ends up doing this. How much faster does he get across, or is it at the same time? He clearly goes quite a bit farther, though, right? 5 times farther? Because the river's 5 times faster? All this will be answered next week on. Yeah. So, relative motion. In trying to answer the posed problem, we need to define what relative motion is. Suppose you're traveling in a car and are being observed by a highway patrolman sitting by the side of the road as shown in figure 325, which conveniently is on the next page. So just flip the page over. Okay? And those of you that don't have this, you will see on that next page, you see a car. It's kind of a 3D kind of deal here. And then here's another car like this, and it's traveling down the road like that. Okay? And the cop car, this is the cops here, and the cop is stopped side of the road, and this car is traveling at 140 kilometers an hour. Speeding. Okay? Okay. So suppose you're traveling in a car and it's being observed by a highway patrolman sitting by the side of the road as shown in figure 325. The patrolman will measure your velocity relative to his position. Remember that whole bit in early on in grade 11 about frame of reference?
Yeah.
Okay, so that's the same idea here, right? In this case, the patrolman is not moving. Let's assume the velocity he measures is 140 kilometers an hour. Your velocity is said to be 140 kilometers an hour east, measured relative to the ground. Everything must be measured relative to something. 99% of the time, when you just give it a value, it's always going to be relative to the ground. Now suppose you pass the patrol car with a velocity of 140 while it is moving with a velocity of 100 in the same direction. Okay, so here's the world's stupidest speeder. Okay, so it's a two-lane highway. Here's the cops going this way at 100, and you decide to pass him doing 140. Side note, I've been in a car that was actually past a police car. He was doing 95. We did 98 as we passed him. We got pulled over. It was very annoying.
So just don't pass police.
Don't pass police. All right. So while the patrol car has, you pass the patrol car with a velocity of 140, while it's moving with a velocity of 100 in the same direction. This time the velocity measured is 40 kilometers an hour relative to the patrol car, right? So his radar, as you go whizzing past him, can I do this? No, I can't. I should have made a different color, shouldn't I? All right, as you travel past 140, what is he going to register you at? What's the radar cam on his, as you go past him like this, what's he going to see?
40.
Going to see 40, right? Relative to him. Even though you're still doing 140 and you're going to get a ticket. Right? Unless he's asleep. He or she. Notice that your velocity is the same, but the two measurements done by the patrolman are different. The bottom line is that a velocity value is measured relative to a reference frame. In everyday use, we are accustomed to using the ground as our stationary reference frame. This frame is implied in most problem situations. So in other words, 99% of the time, it's already relative to the ground. Okay? Now, this just doesn't appear in the book, but let's flip this car around.
Whoa.
So now you're traveling. Let's just extend the road a bit here. You're still traveling 140. He's traveling at an upside down 100. Now what does his radar say?
240.
240, correct. You are approaching each other as if one of you were traveling at 240 and the other was stopped. Okay? So it does depend on your frame of reference.
And you gotta stop it. You're going
Way too fast. Okay. Blah, 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 blah. On page 96 is the absolute worst textbook writing I've ever seen in my life. I pointed out, if you ever become a textbook writer, that is the actual bottom standard for writing a textbook. Don't ever do that.
Right, this one?
Okay, where it says VOG, so like velocity OG, and they got VMG and VOM, and they're trying to tell you what they are. Super confusing. Just ignore. I only point it out because it's so terrible. All right. So let's look at example number 7. Now you guys have example number 7 on the sheet, right? So those of you that don't have a book can now actually sort of follow along. And I do apologize for not having that well prepared. Okay, so relative motion, one dimension. This is really a 30S review. In fact, it's probably grade 10 review. So we won't spend a lot of time. In one dimension, the river problem has 3 possible cases, shown in figure 326. When the river flows, its velocity is 1 meter per second east, and Tarzana can swim at 2 meters per second in still water. So case number 1, Tarzana swims in a dammed up river and there is no current, right? So if there's no current, and Tarzana can swim at 2 meters per second, then what's the resultant? What's her overall resultant speed? Well, it's just 2, right? How come? There's no current. The resultant velocity is just 2. She's swimming at 2 meters per second. Simple. Case number 2, Tarzana swims with the current because the dam broke. And what is the current? Well, it's 1, right? In fact, I'm doing this with my grade 11s right now. So the resultant is going to be 2 meters per second plus 1 meter per second, which is simply what? Big surprise, 3 meters per second. Review, right? It's getting you up to speed, if you'll pardon the expression. If you're against the current, your resultant is going to be 2 meters per second. Plus, this time it's going to be minus 1 meter per second. Remember putting things tip to tail? Remember doing that? Right? And so here the resultant is going to be just 1 meter per second. Just easy, easy stuff. Right? Yeah. Basically, all we're going to do today is sort of do these word problems, but we're going to do them in component format. So I'm just kind of reviewing some word problem stuff is really what's happening. Okay, flip the page, bunch of mumbo jumbo there. They made it far more complicated than they need to. They took a page and a half to do what I took a few little pictures. Page 99, two-dimensional relative velocity. We've learned that when we use vector equations in 2 dimensions, values cannot be substituted in the equation directly. This is because the vector quantities are no longer collinear, they're not in the same straight line. The vector equation tells you how to draw the vector diagram. The plus sign in the equation tells you to connect the vectors head to tail. When you do it by components, you just got to add those x's and y's, right? I mean, even that stuff there at the top of page 99 is kind of blah, 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 blah. Let's go straight to example 8. Relative motion in 2 dimensions. Assume Tarzan can swim at 2 meters per second. The current is 1 meter per second east, and Tarzan is seen to swim directly across. Okay. Terribly worded. What they mean is this. He aims upstream, right? He goes like this, aims upstream. Because of the current, he ends up going straight across. So the resultant in this case is not the hypotenuse like you're used to, which always confuses students. Okay? So Tarzan is the black one here, and the current is in red, and the resultant is in blue. Okay? Now they don't even really ask a question. So the question here is, now I'm starting to remember all the things that I wanted to change about this question. So I'll just do it better for next time around, I guess. So I guess the question is, how fast does Tarzan actually go? What is his result? Do we need to do components here at all? Plain right triangle, don't need to do components. So this value here of t is 1. The current, oh no, sorry. That value is what? That value is 2. The red value is 1. I want to know the r value. Okay? So in this case, usually you got like r squared equals a squared plus b squared, right? But in this case, not happening. That's what I hate about this question. Now it's coming all back to me. I got to scrap all this. I think the only reason I keep doing this is because I like making the jokes about Tarzan and the brawny 8 people. Maybe I'll just read that part and then say that's stupid. We're throwing that textbook away. So in this case here, t squared is going to be c squared plus r squared, right? Because the hypotenuse is the t here. So this is going to be 2 squared is equal to 1 squared plus r squared. And you can solve that, I'm hoping. R squared is going to be 2 squared minus 1 squared. 2 squared is 4, minus 1 squared is 1. That's going to be the square root of 3, or 1.7, is it? I think so. Yeah. So he ends up only swimming at 1.7 meters per second. He's going slower than if he was swimming in a pool with no current. How come? Yeah, he's fighting the current, right? He's going against the current. He's trying to go 2 meters per second, but the current's pulling back and he's only going 1 meter per second. Here's the second part to the question. What angle would he have to aim at to do that? Yeah, but what number, right? So, I mean, it's just Pythagoras, or it's just a application of trig, right? Theta would be equal to inverse tan. Now, I guess it'd be opposite over adjacent. So opposite here is the C, which is the 1. And the resultant here is the adjacent, which is this value that we got, 1.7. And you should get an angle of north 30 west. And the reason I don't like this question is because it kind of asks you for part of each, like it asks you for this value, but it gives you that direction. Then you got to find the direction for that one. I don't like this question. Now it's all coming back. What's case number 2? You guys probably have them on the same side there, right? Okay. Case number 2, Tarzana swims at 2 meters per second. The current is 1 meter per second east. Tarzana is seen to direct her body directly across north. In other words, she aims north but ends up going downstream. So what happens to her? So let's draw the picture. T2, I guess. Current takes her downstream. What is her resultant? Well, now the resultant is actually the hypotenuse, isn't it? That's 1. This is 2. What's the value of r? R squared is equal to 2 squared plus 1 squared. Here we got 4 plus 1, so r is going to be the square root of 5. It's going to be bigger than 2, isn't it? 2.2. Tarzan is clearly swimming faster than Tarzan. But remember, she has to go farther, doesn't she? What angle does she end up going at? Is it 30 degrees? You kind of feel like it should be, don't you? Inverse tan, let's go opposite over adjacent. Opposite is 1, adjacent is 2. Oh, tan of 1/2? 27. It's not 30. North 27 east. So she's going faster and at a different angle. What about cheetah? Faithful briny ape pet. How much faster does he go? I could probably put this on that same page, I guess. Cheetah swims at 2 meters per second, but the current is 5. He points directly north and ends up going downstream. See, and then here again they confuse me because I use a big C for cheetah. Small c for current, which is now 5 because it's during the floods. There's the result, right? 2, 5. What's the r value? Is it going to be 5 times? We can probably just go 2 squared plus 5 squared. R for cheetah is 5.4. How much faster is that than Tarzana? What was she? 2.2. Doesn't look like 5 times faster, does it? Sometimes it just isn't faster what you expect. Yeah, 2.45 times. And of course, you could find that angle as well, right? Is this kind of stuff all coming back to you a little bit? Opposite over adjacent, 5 over 2. It's going to be north 68 east. Okay. On page 101, they talk about who finishes first in the race then. find out, we need to look at the three vector diagrams which are shown together in figure 335. The equation v equals d over t rearranged to find time becomes t equals d over v. We now need to find out which v to use. If you look at the diagrams in figure 335, the velocity vector that points in the direction of the desired motion, north in our case, is the appropriate choice. The other vectors involve the motion of the current, which does nothing to help anyone cross the other side. So in other words, Tarzan swims at 1.7 meters per second in the north direction. So I'm just going to redraw this. I don't know if you guys have room for this or not, but Tarzan, T1, his speed was 1.7 straight across, right? Tarzana, T2, she ended up going downstream, but her velocity that goes straight across was actually equal to 2, right? Her swimming speed. She was going at 2 across. That's the component that's going across the river. And Cheetah, well, his was also 2. So in other words, Tarzana and Cheetah arrive at the same time, or in the same amount of time. And Tarzan, he's going to be behind them. How come? Yeah, they let the current take them, right? They used all of their possible 2 meters per second to get across. They just ended up downstream. They didn't care. They were just trying to get there the fastest, right? Whereas Tarzan, he cared more about where he ended up, and he actually used up some energy going against the current. He actually goes slow. So it's not the same.
I was off, but
You were off by a little bit, yeah. It's okay. Most people think they're going to be at the same time. Okay. None of that is overly relevant to what we're doing, but it's an interesting sort of problem and a good sort of introduction to sort of remembering all this sort of stuff. But let's look at example 9, which isn't terrible, but there is a really bad mistake in there. Which is why I've stopped using this textbook so much. Okay, so relative velocity of outgoing planes. Last one, then I'll be quiet. A pilot with a heading of north 30 east and an airspeed of 400 kilometers an hour flies into a wind coming from the north at 110. You have to be careful with wind speed because some books tell you which direction it's coming from, and some of them tell you which direction it's blowing. Okay, so you have to read carefully. So from the north really means south at 110, right? The wind is 110 south. What is the plane's velocity relative to the ground? In other words, an observer on the ground that is at rest. And how long would it take to complete a journey of 1,000 kilometers at north 30 east? Okay. So in other words, we're trying to find here the resultant of 400 kilometers an hour at north 30 east, along with a velocity of 110 at south. Should we do it by components? Yes, let's do it by components. Because we have no other way to deal with this type of thing other than with a protractor. So I've already drawn the wind speed. It doesn't matter what order we put them in, so let's find the x and the y components here. How much room do you guys have? Half a page? Okay, we should be okay. Don't write too big. I'm going to say wind x. What's the x component of the wind? Is it going left or right? It is not. So the x component of the wind is 0. And conveniently, the y component of the wind is going to be minus 110. Why minus? Because it's down. Do I have to switch to meters per second? Because a lot of the times you do. They're all in kilometers an hour. There's no accelerations. There's no mention to seconds or anything like that. So we can leave it in kilometers per hour. Okay, so now our plane speed of north 30 east. So that's going to be north and east, right? And this is plane, which is 400. So I'm going to call this PX, and I'm going to call that PY. Plane X, plane Y. And this angle down here is 30 degrees. Okay, so this is the stuff we've been doing here for a day or so. So PX, keep your X's in the same column, works good. Here the X is opposite, so it's going to be sine 400 sine 30 200. So that's going to be to the right, so positive 200. Ty is going to be 400 cos 30. $346.4. And that's going to be up, so it's positive. Is this vector addition or vector subtraction, Connor? Addition? What are we trying to find? The resultant or one of the plane or the wind? We're trying to find the resultant, so it's going to be vector addition. So we're going to add them. So Rx is going to be 0 plus 200, which I hope you can all do in your head. Ry is going to be, add those in your head. Now, do I have to take care of that negative? I sure do. 346.4 minus 110, so that's going to be 246, 236.4. Right? And now that you have the Rx and the Ry, you're going to draw the diagram out again. So 200 and 236, that's up. So 200 over 236.4 up. There's your resultant there. R squared is Pythagoras, 236.4 squared plus 200 squared. There's the square, there it is. .7 kilometers per hour. And of course, you got to find the angle. Opposite over adjacent, opposite, adjacent. 236.4 over 200. I apologize for the scribbled up small writing. 236.4 divided by 200. And I get 49.7. Let's call it 50. That would be east 50 north. Now, the mistake here is, it says, how long would it take to complete a journey of 1,000 kilometers an hour at north 30 east? Well, would the plane actually travel north 30 east? No, we already figured that out. The plane would end up going east 50 north, wouldn't it? So right in the question, this is typical textbook. Yeah, the author probably had it right, and some editor changed it. That happens. So how long would it take to travel that 1,000 kilometers? Then you would go V bar equals D over T. That speed would be 309.7. Displacement is 1,000. Solve for time. So 1,000 divided by that number, 309.7. It would take 3.2 hours. But it would be at east 50 north, wouldn't it? It wouldn't be at that angle that they mentioned. Alrighty, that is more than enough listening to me. But a couple of announcements here. Okay. Oh, I guess I should say this here too. Remember, vector subtraction occurs when you're finding the plane or the wind and you know the resultant, right? So that's vector subtraction. If you need some help with that, you might be able to do that, but I think I'm going to leave that for today. You've got a sheet here with some exercise on it. It has addition and subtraction at the bottom. There's a QR code at the back and answers on the back. I found, I guess when I did that subtraction practice thing yesterday, I printed it instead of running it off, and it had no answers. So I found the answers. I just put them on the board there. So if you want to look at your vector subtraction sheet from yesterday, the practice ones, the answers are on the board there. I do have solutions for them if you want. You did get the vector hand in, I think, yesterday, right? Which had an addition and subtraction. If you could get that to me by Friday, that would be good. Okay? So I know that many of you are away tomorrow, so Friday is just going to be a work period. Monday, no school for you guys. Tuesday, more review kind of thing, and test on Wednesday. So those of you that are away tomorrow with the band, make sure you take some physics home for the weekend. I didn't get to marking those hand and kinematics ones yesterday, but I'll try to get to them tonight. If you have not got that to me yet, I need it tomorrow. Get her done. You can got the rest of this period, and you got tomorrow to do that. And I'd really like that vector pretest one done as well. Okay? That all make sense? All right, time for me to be quiet.